Alright guys, welcome to Quantitative Data Part 2. Just a disclaimer, when it comes to the math part, it's obviously not going to be ideal in this just because I don't have a tablet. I would recommend looking at the screen and you can kind of watch the formula as it's glanced over here, or you could just do the practice by yourself. Don't really have good advice for that, but doing my best and I'll describe it as best I can. So, the overview just of this one. We already went through visualizing distribution, now we're going to go through memorizing it. Sorry, we already went through a simple summarization. Now we're going to get into visualization and measuring, specifically how to represent data visually, depending on type, right? Nominal, ordinal, and continuous, recognizing skew and modality, and how to calculate or interpret measures of variability, right? Range, interquartile range, deviation, variance, and standard deviation. I'll probably be asking you to look at the screen every now and then. I'd recommend doing it. You don't have to if you don't want to. Let's get into it. So, nominal data. Again, remember, we have our levels of measurement. We have nominal, we have ordinal, we have interval, and we have ratio. Right now we're looking at nominal. So again, nominal, we have categories that people are in that can't be ordered. Often you want to count people in each category. Frequency tables give us the ability to do that in a nice little table way. So here we're looking at a bunch of different majors, and then let's say we had a data set. We're counting the frequency for the occurrence of each of those majors, and then we're figuring out the percentage that these all collectively take up. That percentage should be out of 100. But anyway, the frequency table shows us discrete data values, right? Categorical data along with the frequency of each. You can use it for ordinal or discrete data. It's very useful. You tally each value, then record the total frequency in the frequency volume. Very, very simple stuff. But you usually want to put this in a prettier format, and that's when we get into below. So bar charts, for example. If you look at the screen, we have our majors up here in our frequency table, and then we have what the bar chart is here. The bar chart is mapping out the frequency on the left on the y-axis, and the majors on the x-axis. So the bar charts are being used to show the frequency of categories. The bars are not connected. This is important since categories are independent. Disconnected bars are a way to show us the data isn't continuous and people are in separate categories. We also have things like pie charts, right? If you look back here, we had our majors and we had our percentages. Like I mentioned, they're supposed to add up to 100. The pie charts are mapping out our majors with our percentages. They show percentages as opposed to raw frequency. They're best. Pie charts are the best for highlighting a relative proportion to the whole. Unfortunately, naturally, when you use pie charts, you lose raw numbers. You can't tell how many people were actually in the data set. There are ways to get around it, like you could put the raw numbers with percent underneath if you want, but it just kind of looks worth. People don't really do that, so you usually lose those raw numbers with pie charts, even though it's the best at highlighting proportions to whole. That's kind of the trade-off. Both pie charts and bar charts can technically display percentage or frequency, but again, it looks worse if you try to do both, and you kind of want to make it clear what you're displaying. That's key to describing quantitative data in these kind of infographics and these kind of different kinds of displays. So you really want to be clear with what you're describing. So that was nominal data and our categorical approach to visualization. Let's get into ordinal or discrete data. So when we make frequency tables for ordinal or discrete data, it doesn't just have the thing we're measuring, its frequency and its percent. It also adds another column, cumulative percent. So again, like we have written here, we can use frequency tables for discrete quantitative data. It also includes cumulative percent, which only makes sense when data has an inherent order, again, because it kind of exponentially builds on itself. Not exponentially, but it cumulatively builds upon itself. Again, we're kind of counting everything as we go. If you look at the screen, as opposed to just having like raw percentile or cumulative percent is when it comes to having zeros, it's all zeros. But once we have one coffee cup, there were 2 people that had 1 coffee cup. So 20% of our data is those people having 2 coffee cups, and so we're at 20% total. But next in our next row here, we're looking at the amount of people who had 2 coffee cups, and it looks like 4 people had 2 coffee cups. That's 40%. 40% of people in our data had had two coffee cups. But now, because we have that 40% on top of our 20%, now our cumulative percent is 60. And then we do it again. We go to the next one, 3 to 20. Now we're at 80. 4 cups, one person did it. That's 10% of our time. Now we have 90. Yada 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 until we get to 100. So bar charts, I keep saying bar like a combination of bar and pi. The bar charts for our ordinal or discrete frequency tables, again, they're not connected, signaling the discrete nature of the values just like before. It's appropriate when participants must choose for whole numbers, right? 0 cups, 1 cups, 2 cups, again, just like our nominal data. Again, it's categorical. Now, let's get into continuous data, right? Again, there we had our nominal data and we had our discrete data, or ordinal / discrete data. But now we're getting into our continuous data here. So we have an example data set here. It's an elaborate string of numbers. It doesn't really matter what it is. Yeah. Just a second here. Just going to review one slide from just a second ago that I am curious about. Okay. Yeah. Anywho, back to it. Yeah. So we had gone through our nominal data frequency tables, our ordinal and discrete data frequency tables. Again, it can be used for both. Yeah. And then we are now looking at our continuous data. So we have this data set, a lot of numbers here. Frequency table is kind of less useful when it comes to continuous data. We display it the same way we did our ordinal data, where we have our our class or frequency or percent or cumulative percent. Yeah. So unless we group people into categories or classes, it's not really too useful. Once we start grouping people into categories or classes, which is called binning, that's when it becomes useful. And that's where we get histograms. So it kind of becomes a visual representation of grouped continuous data showing frequencies of classes. So again, we showed this in the frequency table up here, but we kind of have because it's on a continuum, we kind of group and we class different sections of that continuum. So because of that, in the histogram, as you look at the screen here, the bars are actually connected, reflecting the continuity of the variable. It indicates that people were able to obtain any score from 1 to 80 without the values being entirely discrete. You lose some information because you don't know about the specific values you gain, or the specific values, but you gain some awareness of distribution and variability. Yeah, so we have our scores here. We have our frequency. We can see that it's all kind of classed through. So that's the benefit of histograms. You get an overall shape and a much larger idea of distribution. That's the benefit of histograms, right? Much larger idea of distribution. So when we look at distribution, let's look at distribution, right? So just to go through what we've gone through again, we went through our ordinal and discrete data, our nominal data, our continuous data, all in the context of frequency tables and kind of infographics and different methods of displaying its data that looks good. Just a second here. Skip like 1 minute in advance. Okay, yeah. So we've gone through our nominal data and our ordinal or discrete data and our continuous data, all demonstrating the frequency tables that are kind of best used for them and the substitutes for frequency tables that we can use, whether that be bar and pi charts for our nominal data, bar charts for our ordinal and discrete data, and then our histograms for our continuous data. Now we can look at our distribution shapes. So again, histograms give us a good overall shape and a much larger idea of distribution. So let's analyze our distribution. If we look at the screen, you can see a good example of distribution. We have distribution is essentially just demonstrating how data is distributed across a range of like in a graph, for example. And there's a concept in distribution called skewness, and this is referring to the side of distribution where there is a dominant skew of our data set. So how many scores on one side of distribution uh, are on one side of distribution as opposed to the other side. So we have negative skews and we have positive skews. Negative skews are also known as left skews. Positive skews are also known as right skews. Negative skews or left skews, the longer side of the skew tail is on the left. This is the negative side on a number line, right? So if we look at the examples here, the concentration of the data, I guess on the x-axis would typically be higher in value, specifically just because again there's an outlier. There's an outlier pulling the data in the direction that is opposite to the tail. I know I'm not explaining it too well. If you look at the screen, it's pretty clear. In a positive skew, it's a right skew. The longer tail is on the right. There's an outlier pulling the data more to the left, more to the start of the x-axis. In the negative left skew, there is a longer tail on the left because there's an outlier pulling the data to the right, further along the x-axis. Yeah. Okay, so measures of central tendency and skew, right, are mean, median, mode. If you look at this here, in symmetrical distribution, meaning everything's equal, it's like a proper curve up and down, equally symmetrical. Mean, median, mode all in the same place. But when you get a positive skew, meaning again the tail is on the right, you kind of get this dynamic where, like usual, you have your mode at the top of the peak of your data skew, followed by the median, kind of middling the mode and the mean, with the mean facing towards the right side of the positive skew, towards the tail, and then you get the opposite effect with the tail on the left. Confusing if you look at it, very clear. I was literally just describing the image here, but let's actually get into describing what exactly it is that I just said. So essentially, the mean is very sensitive to outliers, always pulling it in the direction of the tail. So again, we have a positive negative skew. The mean is very sensitive to outliers. We are going to get a pull of the mean into the direction of the tail. It's kind of in the balancing point of the skew, right? If you were going to balance the skew on your finger, if we imagine this as a physical object, the mean would be the balancing point. So the mode is always at the peak of the skew. And so naturally, that's not its peak point of balance because of weight distribution, right? So the mean is technically going to be in the middle of its weight, and then the mode is kind of going to be always in between the mean and the median. Sorry, the mean and the mode. The median, again, it's balancing the two sort of weighted areas on the skew. It's dividing that area. We should consider using the median when describing data over the mean in this case, because it'll provide us with a better idea of the typical value, right? We already knew this. We should consider using the median over the mean when there are outliers. Yeah, so again, Median over mean because it can give us a typical value. Median over mean usually because there are outliers, assuming that's something that we want to paint a more proper picture of. Yeah, outliers can increase the mean but don't have much effect on the median. That's kind of why. And just the last thing about interpreting the skew here, if the mean is greater than the median, meaning it's further along the x-axis, the data is positively skewed, or right skewed, right? The tail is going to the right. If the mean is less than the median, meaning again the mean is following the left tail, it is negatively skewed, right? If you look at the screen here, it's pretty blatantly simple. We'll talk about mode in a second here, but just know for now that when we have a nicely shaped skew data like this, the mode, like I said, will always cap the curve. It'll be the largest value in the data set, right before the median, kind of on the opposite side of the mean, with the median centering the other two. Very easily displayed here, but the key takeaway for this is just the positive and the negative skew, and then the mode always capping the curve, the median kind of acting as the balancing point and being a better measure than the mean typically if we want to avoid outliers, if we want to get a sense of the typical value. Yeah, the mean is the balancing point. The median acts as a balance between the mean and the mode. Yeah, but take away the positive and the negative skew. Again, if the tail's going to the right, it's positive skew. If the tail's going to the left, it's a negative skew. The mean is going to act as the balancing point. The median will be a better typical representation of value. If there are outliers, it'll represent the data better, and the mode is always capping the curve. Just remember all that. So let's actually specify mode, right? When it comes to interpreting skew, reading these kind of skewed graphs, these histograms here, in distributive shapes and distribution shapes. If we have one peak, it's unimodal. If we have two peaks that are approximately equal, it's bimodal. If we have approximately three, it's multimodal. Yeah, so unimodal is one highest frequency or value. Here we know whichever score on the x-axis with the peak is the mode, though we don't always know the exact score. Yeah, we know whichever score on the x-axis coincides with the peak is the mode, is what I meant to say. Bimodal, we have two approximately equal high frequencies. Multimodal, multi of them. Multi and bi can be pretty subjective, but it could be fairly obvious too. The mode will always be the highest point. We already talked about that. It's useful both for categorical, meaning most common value, and continuous data, which is peaks and distribution curve, which can have more than one mode. So this is when we get into some of the more mathy stuff. So stay with me. Measures of variability. So we've kind of been getting into discrete data. We've been getting into... I'm tripping. We haven't been. It's pretty much all been continuous. There's been some discrete, like the nominal and ordinal stuff. That's discrete, but everything else pretty much fully continuous. And this is not going to change that. So measures of variability, it's more so with continuous data than discrete data. Measures of variability statistics describe how spread out values are around a central point. They're usually a standard deviation paired with some kind of measure of central tendency. Again, some of those examples are range, interquartile range, deviation, variance, and standard deviation. Range, deviation, and interquartile range are mostly revolving around mean analysis, and variance and standard deviation. Deviation, variation, and standard deviation are generally about the mean, and range and interquartile range are generally about the median. We rarely report on variance though. But yeah, let's get into these different measures of variability. So range is very simple. Range is max minus min. You take the biggest score and you minus the smallest score in a data set, for example. Largest value minus smallest value. Ordering data helps find the lowest and highest, but it's not really necessary. We're going to be using this data set of PCL scores. So the data set, just so we know, is 22, 26, 33, 34, 36, 36, 38. Not too relevant. If you just look at the screen and you remember what I just said, you'll probably remember it though, but yeah. So again, range is just max minus min, big minus small, large minus smallest. The limitation, highly sensitive to outliers. That's why it's so nice to put with a median. And smaller samples often yield smaller ranges. Interquartile range. So this is when we get into something a little bit more complicated. So interquartile range, or IQR, focuses on the middle 50% of data between quartile 1 and quartile 3. So it's measuring the point between 25% of the data and 75% of the data. Interquartile range, again, just so we remember, it's measuring between quartile 1 and 3, so the IQR formula is Q3 minus Q1. If you look at the screen, you'll see this little example here. We split a graph of like 100% of our data, like a representation of 100% of our data into 4 quadrants. 25, 25, 25, 25. This is split into 3 different quartiles, with quartile 2 being the median. So quartiles are positions in a range of values representing multiples of 25. The median, again, is the second quartile. It falls at 50% of the score. The first quartile is 25% of the scores fall below Q1, 75% fall above. Again, because it's sitting at the 25% line, 25% below, 75% above. Third quartile, 75% of scores fall below, 25% are above, because again, it's sitting at quadrant 3 or 75%. IQR is less affected than extreme values, and also helpful for identifying outliers. It's important to note that Q1 and 3 are not outliers. What is expanded beyond them technically are the outliers, and we'll look at that. So again, we have all of this foundational understanding. Let's use it. People like to use IQR to find outliers. The formula for detecting that is scores that are greater. So if we have a data set, scores that are greater than third quartile plus, in brackets, 1.5 times the IQR are high-end outliers, as they're outside of your upper fence, right? Scores that are greater than Q3, right? Upper fence. Scores that are less than Q1, this is looking at our lower fence, again, less than Q1. Scores that are less than Q1 minus, in brackets, 1.5 times IQR are low-end outliers, as they're outside of the lower fence. Let's look at the example below, okay? So this is using box plots or box and whisker plots. It really only works with unimodal data, but for our purposes, it's fine. Please look at the screen. I would highly recommend it. Just as an example, so again, this is our interquartile range representation here, and then these are our box and whisker plots. So you can see the components of this is we have our upper hinge at Q3, lower hinge at Q1, median at Q2. We understand that. Then we have our upper fence, and the upper fence formula again at Q3 plus 1.5 times IQR. Lower fence is Q1 minus 1.5 times IQR. Our whiskers, because it's a box and whisker, the box is that Q1 to Q3 range. The whisker is the largest value within our upper fence and the smallest value within our lower fence. So anything within a data set that is within our whiskers, so the largest value in the upper fence and the smallest value in the lower fence and everything in between, that is all valid data. Everything else is an outlier, so everything that falls beyond our fences. That's a good representation of the box and whiskers. The advantage of box and whiskers, it includes all data, clearly marks outliers, and allows comparison between groups. this little thing I have here, it's just a reminder when it comes to test questions, be mindful of the fact that you might be asked, specifically when drawing a box and whisker plot, the line in the middle of the box, Q2, will be at, for example, blank. The left whisker will extend from a point to blank, and the right whisker will extend from a point to blank. So if you look at the screen, you'll understand. They give us values here, though, so we can work on this question theoretically here. So when we have a question like this, when it's asking what it's asking for is not only the median, but how far the different quartiles can include numbers in our data set with outliers ignored. So yeah. So again, we want to find the median. So we're going to take our data set. We're going to order that. Our median we're going to know is 5. So we know that our median is 5. Just a second here. Sorry about that. Yeah, so our data here is, our median here is 5, because we ordered our data and we determined what the median is. Then, if past that we want to find our outliers, we would first look at our upper fence, right? So we would take our Q3. We know that our Q3 from what they give us, our Q3 is 6. So 6 plus 1.5 times the IQR. The IQR is Q3 minus Q1, so that would be 6 minus 2. The IQR is 4. So to find our upper fence, it is 6 plus 1.5 times 4. That number will be 12. In our data set, the closest number we have to 12 is 9, but we have an outlier which is 18. So when it's asking us what the right whisker will extend from Q3 to, we know that it will extend to 9, right? That is the closest number to our upper fence. When it comes to our lower fence, the answer to that, if we apply the same principle from earlier, lower fence being Q1 minus 1.5 times IQR, in this question it is 2 minus 1.5 times 4. That lower fence will be negative 4. The closest number we have to that is 0, and we have no outliers, so the answer would be, our median would be 5. Our upper fence, our whisker would extend from Q1 to 0, and our right positive whisker would extend from Q3 to 9. I hope that worked. When we look at this question here, it's just showing us a box and whisker plot with the median plotted out, and it's asking, if we look at the kind of box and whisker plot, what kind of, I think it's asking what kind of skew we're looking at. If we just take the representation here and we just kind of like turn it on its side, we can evaluate the data. So just turn it right, and then see which way the long side of the box and whisker plot is facing. In this case, it is facing towards the left. As we know, if the box and whisker plot has its tail facing towards the left, it is negatively skewed. Okay. Deviation. Let's get into that, right? So all of that, all the box and whisker stuff, that was all interquartile range. So we've gone through range and interquartile range. Let's get into deviation. So deviation is the difference between each score and the mean of the data set. Again, we calculate the deviation because we want to determine how spread out the score is from the mean. There are two different kinds of deviation data sets, population and sample. Population data set, the deviation of the what is that? What would xi be? What does that mean? I think it's just our data. Yeah. So the population data set, the deviation formula would just be the deviation of the number equals the number minus our mean. Yeah. Minus our population mean, and the sample data set is the number minus our sample mean. Did not do a good job of explaining that. But yeah, so there are two different kinds of deviation data sets, population data sets and sample data sets. When it comes to population data sets, the deviation of our data is the data that we're looking at, the piece of data, like the score, for example. If we're looking at PCL scores, right, that instance of data, minus the population mean. And for sample data sets, it is that individual score minus the sample mean. Yeah, so we get those values. Let's find the deviation. So first, find the mean score. That's a very long-winded way of saying what I'm about to say. So first, let's find the mean, right? If we're looking at PCL, remember it's 38, 33, 22, 36, 34, 36, 36. If you look at the screen, you'll be able to see. Let's find the mean, right? Add them all together, divide them by the amount of numbers that we have. We get 32.14. If we want to find the deviation for each score, we take our score minus that mean. Yeah, pretty simple. So that's our deviation. So deviation shows the dispersion around the mean, unlike IQR or box plots, which shows dispersion around the median. Range in IQR always gets paired with median. Deviation is always paired with mean. That's important to note. Okay, so now we have gone through range, interquartile range, deviation. Now let's get into some variation. So variation is defined as the average square deviation from the mean. Again, give single number to assess deviation of data. We don't usually use this though because the number is too big. We instead use sample. Standard deviation. Yeah. So again, variance, average square division from the mean gives a single number to assess the deviation of the data, but the number is usually too big, so I don't really use it. But let's look at it. So what's the variance formula? For sample variance, the sample variance is the it's this formula called the sum of squares. So it's our sigma notation times times our deviation. Yeah, right. Yes. Yes. Okay. So the formula for variance is, if you look at the screen, it's right there. Just look at that. But it's our sigma notation times our deviation for each entry. All of that squared divided by the number of values minus 1. That one formula, the sigma notation times our deviation squared is called the sum of squares. So population variance is the same thing, but for its formula, if it's again just substituting values. So sigma notation times deviation for the population instead of the sample squared over the population size. Yeah, so it's each score minus the mean squared divided by sample size minus 1 or population size minus 1. Again, the variance formula is each score minus the mean squared divided by sample size minus 1 or population size minus 1. In words, if you wanted to find your variance step by step, you'd want to find the mean of the sample data set, then find the deviation of each entry, square each deviation, add to get the sum of the squares, and then divide by n minus 1 to get the sample variance. Yeah. Yeah, this is rarely reported directly because, again, it's in squared units. Variance is hard to interpret. Remember, when it comes to this, we are generally trying to say the difference from the mean. This doesn't do that, though, because the number's too big and has never been unsquared. Again, instead we typically report standard deviation because it squares the variance, square roots the variance. Again, just simply squaring the variance, the number ends up being too big, we want to square root that. That's what standard deviation gives us the ability to do. So, standard deviation is the most widely used variability measure. It's defined as the square root of variance. It is the measure of the spread of scores out from the mean of the sample. So, you are literally, the formula is square rooting the variance formula. Follow previous listed steps 1 to 5. Just finding the variance, find the square root of the variance to get the sample standard deviation after that. Pretty simple, but very common, very effective. So again, our measures of variability were range, interquartile range, deviation, variation, and standard deviation. One last thing, when it comes to interpreting standard deviation is a measure of the typical amount of entry deviates. It's the typical amount an entry deviates from the mean. Thus, the more the entries are spread out, the greater the standard deviation. Again, the more the entries are spread out from the mean, the greater the standard deviation. If you look at the screen, we can see a representation of that right there. By the way, if you wanted to look at the screen about the standard deviation, it's all right here. And if you wanted to look for the variance, it's all right here. But yeah, a larger standard deviation is a greater spread, more heterogeneity in responses, right? More differences. Smaller standard deviation, tighter clusters, more homogeneity. Standard deviation is helpful in these displays because it's essentially, it is essential in comparing different groups or conditions in their variance. Yeah. My personal advice would be, when it comes to this one chapter in specific, don't use the podcast notes. Do the practice, review your content, do some practice questions, and you'll be good. Yeah.